previous lecture we have talked about introduced heat capacity, and we have told that there are two types of heat capacity at constant volume and heat capacity at constant pressure. So Cv is heat capacity at constant volume, Cp is heat capacity at constant pressure. We have introduced the concept of enthalpy, and then we told what is the, we ended here, we told what will be the Cp minus Cv, or difference between heat capacity at constant pressure and heat capacity at constant volume for an ideal gas. So if we want to do that, so as we know, if we recall, Cp is del H del T, H is enthalpy, del H del T at constant pressure, and Cv is del U del T at constant volume. Now for ideal gas it becomes pretty easy because you have the equation of state, right? This is the equation of state. Now you know del W, this is reversible work obviously, is equals to minus PdV, and it's mechanical work. And you also know from first law that du equals to delta Q plus delta W. Now since you know that, you will also know delta Q, which is the heat input, is equals to du plus PdV, because del W is minus PdV if the work done on the system is positive, and del W is minus PdV. This we already have found out. So delta Q is du plus PdV. Du is Cv dt plus PdV, right? Because as you see from this definition, from the definition here, that du is nothing but Cv dt, and you have PdV, right? Now you see delta Q, if I tell constant pressure, that means P is constant, then I can write delta Q is nothing but basically it's like delta Qp is nothing but dH, which is nothing but Cp dt. So du is Cv dt and delta Q is Cp dt. So you can see now you have dt here, you have dt here, you have dt here, and you have Cp dt equals to Cv dt plus PdV. Now PdV I have changed to nRdt. You can easily see. So you have PV equals to nRT, you have PdV plus VdP. From PV you can write PdV plus VdP, like this is basically nothing but d of PV, which is equals to PdV plus VdP, which is equals to, now this dPV is dnRT. Now if n is constant, if pressure is constant and n is also constant, that is the mole number is constant, then you have you see R is anyway constant, it's universal gas constant, and so you have RT dn. This RT dn term will go to 0 because n is constant. So PdV plus VdP. Now if pressure is constant, then VdP, this term will go to 0, right? So you have PdV, which is equals to nRdt, right? PdV equals to nRdt, and so you have substituted here. So you have got Cp dt, you got Cp dt, Cv dt, and nRdt. Now you can rearrange and you can write Cp minus Cv equals to nR. Remember, n is the number of moles of the ideal gas. However, when it comes to non-ideal gases or any other substance, you will see that it becomes slightly more complex. In fact, knowing the definition of entropy becomes very useful there, or applying Maxwell relations that we will learn soon will be useful there. So I will come back to that, but please remember that there is a difference in heat capacity at constant pressure and heat capacity at constant volume, and for ideal gas that difference is equal to nR, right? Now remember, we are talking about ideal gases, but we know that ideal gases there is no interaction force between the ideal gas molecules, right? That's the idea. Ideal gas atoms do not interact with each other, that is, there is no force of interaction between them. However, for real gases, you have interactions, right, between the constituent atoms. That is, there is a force of interaction between the constituent atoms or molecules. Now, in such a case, u is also a function of v. See, the problem is when you have no interactions, then basically we can tell that in such a case the change in internal energy is only because of changing temperature. Change in volume or basically pressure does not affect it. But when it comes to as you know, as you recall, that u is an exact du is an exact differential, and du equals to, if I tell u is a function of t and v, for example, if I tell u is a function of t and v, we can write du equals to del u del t v dt plus del u del v constant temperature dv, right? And this part, this one is your Cv, right? This is equal to your Cv. So basically, you can write this is equal to Cv dt, and and del u del v t. Let me call it pi. Del u del v t. Let's call it pi t plus pi t. Now, as you can see, that the change in energy is related to the change in temperature, and that is the relation that in that relation what you get is Cv at constant volume, and if you use constant temperature, you have something called pi t, which is like pressure. Now, in such a case, this pi t basically becomes non-zero when you have interacting gases or real gases. In ideal gases, pi t is 0, because in ideal gases, the interaction force between constituent molecules or atoms is not there. So there is only kinetic energy, there is only temperature that is relevant, and change in temperature, and change in temperature causes change in internal energy of the ideal gas. However, change in pressure, so change in volume does not. Change in volume does not. Now, if there is change in volume, there is no change in internal energy. So, if you now look at it, so if you look at the energy of an ideal gas, which is 3 by 2 RT, again, so this is one thing that I have to tell. 3 by 2, if I tell 3 by 2 RT, this 3 by 2 RT, what's the unit? This is something that R is joules per, R generally is given as joules per mole Kelvin. So, when I am talking about energy of an ideal gas, we are already talking of energy per mole. If I just write 3 by 2 RT. So, if I have to write the energy of an ideal gas containing n moles, it will be 3 by 2 n RT, right? So, basically, that's why there is something called molar heat capacity, which is CVM, which is basically, so here this has to be 3 by 2 n RT, where n is the number of moles. This is something that you have to understand. This will come soon of ideal gas. So, the molar heat capacity is per mole. So, it is Cv, m, which is nothing but Cv by n, where n is the total number of moles of a substance. Now, you see, for a real gas, as I told you, u versus v also has a slope. Now, what type of slope is it, and why is this slope? So, this is something that we have to understand. Now, as you can see, look at this equation. Let us look at this. Let us have a look at this equation first. You have du from your exact differential. You got du equal to Cv dt, where Cv is the heat capacity at constant volume, plus pi t dV, and pi t, and also you know du equals to delta Q minus P dV. If you compare, you see pi t is nothing but minus P, which we can call as internal pressure. Pi t is nothing but an internal pressure, because minus P dV, when we were doing what we were looking at, we are looking at something like this. I have a piston here, and then I had a volume, and the volume was reducing. So initially I had a volume here, right? Initial volume was like V, and then it decreased by an amount of dV, right? There is a decrease in the amount by amount dV, and dV is negative, and P is the external pressure. So as a result, you have to put a minus P dV because work done on the system is positive. That was our convention, according to our convention. Now pi t, if you see, has a negative. It is pi t same as pressure, but pi t has a plus in front of it, right? It has a negative. It's basically pi t has a sign opposite to that of the of P, right? So here P is the external pressure, and pi t is something like an internal pressure. Now if you see what I told, that since there is no interaction in ideal gas, there is no interaction between molecules, no interaction between molecules. As a result, pi t equal to C. However, for real gases, there is interaction between molecules. Now, if that is so, then you have this surface where U is plotted. So you have U going up, and temperature is increasing, as you can see here, and V is decreasing, as you can see here. So as you can see, now look at the slope. Now if it is U versus V, if you look at the slope increases as V decreases, right? So as V is decreasing, the slope is increasing, or internal energy is increasing. Internal energy increases as the volume decreases, right? That is for a real gas. The interactions become more and more effective. Means that the contribution from the interactions increases to the internal energy increases as you decrease the volume, right? As you decrease the volume. On the other hand, as you increase temperature, as you increase temperature, means with temperature, you generally will see that there is a upward slope, right? So basically, if you look at the slope that we are showing here, you can see there is a downward slope. Now if I do U versus T, it should be an upward slope, right? So if I look at, say, U versus T here, this is your, let me brush with another color just to distinguish. Yeah, so if you see, if you have U this axis, U along y axis, and T along x axis, in general, you will see the slope will be going something like this, right? So you go something like this. So you will have a positive slope. So from U, so as V increases, internal energy decreases. So as you can see here, so what you can say here is that as from these curves, or even from this surface, you can tell that as T increases, as T increases, U increases. There will be an increase in U, right? With the increase in temperature, there will be an increase in U. However, as V increases, U will go down, and this is basically true for real gases or real systems with interactions, right? So with increase in temperature, internal energy increases. With increase in volume, internal energy decreases. Okay, so another thing that you have to often you will see that we often refer to something called specific heat. Specific heat in general is defined as heat capacity per unit mass, like heat capacity per gram per Kelvin, or heat capacity per kg per Kelvin, like that. And molar heat capacity is per unit mole, right? It is CVM, for example, is molar heat capacity at constant volume. CPM is molar heat capacity at constant pressure. Now, as you know, Cp minus Cv equals to Nr, where N is the number of moles. So now molar heat capacity Cp N minus Cv molar equals to R, because R is joules, so and it has a unit of joules per mole Kelvin. These are things that you should understand. So, for example, if I take this and if I tell heat capacity, so if I tell specific heat of water at room temperature and 1 atmosphere pressure is 4 joules per Kelvin per gram. Now, if I tell you what will be its molar heat capacity, what will you do? You know, you are talking of water molecule H2O. There are two H atoms. There are in one molecule of water. There are 2 H atoms and 1 O atom. And as you know, H has an atomic mass of 1 atomic mass unit, or you can convert it to grams. Then it becomes 1 gram. And oxygen has 16 grams. So basically, the atomic mass of water in grams, if I tell, 18 grams. Now that means you have 18 grams as the atomic mass, and you have gram here. So you have a unit of 4 joules by Kelvin gram. Now you are telling gram and you want to convert it to mole. So 1 mole of H2O or water contains 18, is basically 18 grams of water. So 1 gram is 1 by 18. So basically this will become 1 gram is basically 1 by 18. So 18 to 4, 72 joules per Kelvin, right? So because the molecular weight of water is 18, right? It is so the molecular weight of water is 18. 1 mole contains 18 grams of water, and 18 grams equal to 1 mole. Therefore, 1 gram equals to 1 by 18 moles. And I am just, instead of 1 gram, I am putting 1 by 18. So 18 into 4, it becomes 18 to 4, which is 72. So 72 joules per Kelvin per mole is the molar heat capacity. It's the molar heat capacity of water. Right? So this is how from specific heat you can go to molar heat capacity. Now you know the relation between Cp and Cv when you have ideal gas, that Cp molar minus Cv molar is equals to R. But what about all substances? Now see, we will now define more measurable quantities. So we already know about what are the measurable quantities T, P, and then Cp and Cv you can obtain using calorimetry. Okay, I will discuss maybe later some principle of calorimetry, but that's you have a standard sample. Based on the standard sample, when you look at how much it is transferred, and you can calculate Cp or Cv, right? You can use like bomb calorimetry and stuff. Now the point is Cp and Cv, there is a difference, it's R for ideal gas, but for in general, what's the relation between Cp and Cv for say any real gas or for solid or for liquid? So in such cases, we need to know two more measurable quantities. One measurable quantity which is of interest is volumetric coefficient of thermal expansion, alpha, right? You often know about the linear coefficient of thermal expansion. Now what we are defining here is the thermal expansion coefficient, that is volumetric. So this is defined as how the volume of a material will change as temperature changes, keeping pressure fixed. So volume change as a function of temperature, keeping pressure fixed, and normalized with the volume itself, volume of the body itself. So it's 1 by V del V del T, which is basically alpha, right? So del V del T, so volume is like centimeter cube, and this is like Kelvin, but you have 1 by V, a normalization, so it's like 1 by centimeter cube. So this becomes, it has the unit of Kelvin inverse. The unit is Kelvin inverse. It's temperature inverse basically. So 1 by V del V del T. Now there is also something called compressibility, or which is represented as beta or kappa T. So kappa T or beta is basically change in volume with respect to change in pressure, again normalized by the volume. So this is called, and remember temperature is kept constant here, so it is called isothermal, means it's a isothermal compressibility. Isothermal, because temperature is kept constant, compressibility. And that is, there is a negative sign here. I will tell you why it becomes, there should be a negative sign here, because we are looking at compression, right? You are looking at compression. And again, as I told you, that as you increase pressure, volume decreases, right? So there is obviously a negative sign that we want to put in here. So it becomes minus 1 by V del V del Pt. Now these are two more measurable quantities. So we are basically finding out different measurable quantities that you can measure as, like, see, thermodynamics in general deal with macroscopic quantities, not molecular level quantities, and in the macroscopic quantities that are measurable are more and more useful, because there will be quantities such as energy, for example, which is not directly measurable, right? But you can measure temperature, you can measure pressure using a parameter, temperature using a thermometer, you can measure use calorimeters to measure heat capacities, whether it is at constant pressure or at constant volume. Also you can measure the coefficient of thermal expansion and coefficient of compressibility. Now if you know how to measure all of these, then you will see we will use Maxwell's relations later, so I am not immediately going to give you the proof, but what I am going to give you is I will state the relations. Cp minus Cv equal to alpha square Tv by kappa T, or alpha square Tv by beta. Now as you can see here, alpha is your coefficient of thermal expansion, kappa T is isothermal compressibility, T is temperature, V is volume. Volume is again measured. Now think of an ideal gas again. In your ideal gas, you know PV equals to nRT. If you look at alpha, in that case, for this PV equal to nRT equation state, you will see alpha is nothing but 1 by T. It's inverse of the temperature for an ideal gas. And kappa T is nothing but 1 by P. Now, if you look at that, like the kappa T is nothing but minus 1 by V del P. So you have alpha square Tv, so it is A naught T by P square V, because V is there, and del V del P is what you are looking at. So you are writing V equals to A naught T by P, so there is a minus sign, so minus, and here there is a minus sign, so it becomes plus, right? This becomes plus. And so then you get nothing but A naught T is PV, PV by P square V is 1 by P, right? So you get this value here, and so you get, if you substitute all of these here, alpha square PV by KT is nothing but PV by T, because 1 by is NR by PV is 1 by T, and there is a T and V, T goes out, there is a V, alpha square, so there is a T square, so V by T by 1 by P, which is PV by T, which is nothing but equal to V. Right? So you can see that this relationship definitely holds for ideal gas, but this relationship holds good for any substance, whether it is liquid water, whether it is a solid ice, whether it is for any material, this relation holds. And where you require to know the alpha, you require to know the isothermal compressibility of the material, and obviously for obvious reasons, let me tell you what will be, say for condensed phases, what will be the isothermal compressibility. How much is the isothermal compressibility? If you know, then you can see how much is the difference between Cp and Cv for solids and liquids in general. Okay, so that's the idea. Only thing I can tell you, since beta is small in general for solids, and alpha is also actually small, but let's think of aluminium, for example. If you see for aluminium, it's aluminium solid, you have, okay, so it's 1 by pressure, so this is Pascal inverse. So for aluminium it is 1.385 10 minus 11. Pascal inverse is your isothermal compressibility, and alpha is 69.3 10 minus 6 per Kelvin. And let us take the temperature T equal to 298 Kelvin, which is basically room temperature, 25 degrees Celsius. And let's take the molar volume of aluminium. Let us assume at 298 Kelvin. Not assume, means you can measure it. You will find that it's approximately 10⁻⁵ meter cube per mole. Now, in such a case, if you add all of these, so basically you get, and 1 atmosphere, as you know, is 101,325 pascals, right? 101,325 pascals. So, if you evaluate this, what you get is like 1 joule per mole Kelvin. Okay, on the one hand, you have like Cp minus Cv, which is R, which is like 8.314 joule per mole Kelvin. On the other hand, for solid aluminium, Cp minus Cv is small, right? Cp minus Cv is small. Many a times we use this approximation of Cp is approximately equal to Cv, or we tell that the PV watt contribution is very small, and we often use one type of its capacity. We use one type of heat capacity, which is basically we substitute. We neither use Cp nor Cv, but we directly tell C for as the heat capacity. Means we tell that Cp minus Cv is small. We can think of heat capacity at constant volume or at constant pressure. Many times we take Cp, heat capacity at constant pressure, as the heat capacity of solids and liquids. So, C is the heat capacity. It can be either Cp or Cv, because Cp minus Cv is small for solids and liquids. So, basically when you tell this, what we tell is basically H equals to U plus PV. PV work for normal pressure conditions, not very high pressure, not like go exceed like 20-30 GPAs of pressure. No, then there will be a pressure induced, a new type of equilibrium will be created where pressure dependence will come in. But here in general for solids, PV work is much smaller. So H can be written as approximately the same as, for this is again for condensed phases, for condensed systems which include liquids and solids. However, as you can see that there is still some difference, like Cp minus Cv is 1 joule per mole Kelvin. It's not really that small, right? So, but it is much smaller if you compare to gases. That's right. Now, I give you some aside here. This is something, this is a part of, means in your solid state physics or in your thermal physics course or something like that, you might have learned about it. So, this is about the heat capacity of solids, right? Heat capacity, there is too long and Petit's law. I think you, some of you might have read it. So, near room temperature, which states that near room temperature is pretty high for physicists. For physicists, they deal with temperatures much below room temperatures, right? They deal with temperatures which are close to like absolute zero. So, they look at temperatures which are like really below the room temperature. So, as a result, where quantum quantum approximations become very relevant, this quantum nature becomes very relevant. You don't use Maxwell-Boltzmann statistics and stuff. You will learn about it more in your solid state physics courses. But here I will give you an aside, because from solid state physics or from the molecular interpretation of thermodynamics, if you look at the molecular version of it or statistical mechanical version of it, you will see that there you are considering atomic description, and you are trying to basically find a bridge between this atomic description and the thermodynamic description, macroscopic thermodynamic description. Now, in such cases, you will see that as you have previously we have defined energy, internal energy, right? Because we told equipartition theorem and we told that all these gas molecules are colliding and there is this translational kinetic energy and there is this 3 by 2 kBT, right? For each gas molecule, they are basically they have in ideal gas. In kinetic theory, for example, you have this equipartition theorem. 3 by 2 kBT on an average for a monoatomic ideal gas is going to be the energy contribution per atom, 3 by 2 kBT, right? Now, these are the translational degrees of freedom. Now, if you have solids, for example, the solids also vibrate, right? It's like solids. You can think of like there are atoms, they are connected by springs, and each atom is like an oscillator. So it is oscillating there, and it is vibrating, and it can vibrate along x direction, along y direction, or z direction, right? So you can have like here also you can have 3 degrees of freedom. Right, if the atom is vibrating, oscillating this way or this way or this way. Now, if you look at that, then basically you have 3 by 2 kBT from the translational degrees of freedom, and from the vibrational degrees you have 3 by 2 kBT. So, energy per atom of a solid we can generally write as 3 kBT. Right? Now, if you look at that, energy is 3 kBT per atom. Heat capacity is del U del T, right? Heat capacity is del U del T. So, basically it is given as 3 kB. That is something that was observed by Dulong and Petit. So, for most solids, means it includes whether it is copper, whether it is lead, whether it is aluminium, it does not matter. It is approximately going to be 3 kB per atom. That was what Dulong and Petit stated. Right. So, basically internal energy, as I told you, per mole will now become 3 kBT Na, where Na is the Avogadro number, and Cv, for example, molar heat capacity, if I tell, it is like del T of 3 kBT Na, which is basically 3 kB Na, which is equal to 3R, right, 3R per mole, right. So, it's molar heat capacity of any solid is like 3R per 3R, right, molar heat capacity is 3R. Now, as I told, each atom is an oscillator with 6 degrees of freedom is something that we are telling that each atom is having a 6 degrees of freedom, but there are two. So, if that is so, on an average, you can think of half kBT contribution for each degree of freedom. So, half kBT, half kBT, half kBT. So, total basically, if you think of that with 6 degrees of freedom means translational as well as vibrational. And total it is 3 kB, right? So, that is how we are looking at it, right? These are atoms connected by springs in all directions. However, it has been observed that the heat capacity continues to decrease as temperature decreases, and heat capacity vanishes at T equal to 0 Kelvin. So, Einstein looked at it. So, basically Dulong and Petit's law can explain the high temperature heat capacity, molar heat capacity of solids. However, as you go to lower temperatures, it cannot explain anything. Dulong and Petit's law does not even hold, right? It does not even hold as you go to lower and lower temperatures. Particularly, you have to remember that it vanishes at T equal to 0 Kelvin. It is quite low, and then it grows and it goes to Dulong and Petit regime, which is the classical regimes. Now, Einstein proposed a model where he considered a solid as a lattice structure. This is obviously correct with n atoms. So, it is like it can be a Fish-Center cubic atom, it can be Fish-Center cubic lattice, it can be a body-centered cubic lattice, simple cubic lattice, tetragonal lattice, whatever. But it is having a lattice structure with certain number of atoms. Now, each atom, what Einstein, again these are assumptions from Einstein's model. So, these are the assumptions. As you can see, solid has a lattice structure, which is correct, right? Solid generally, when we tell crystal structure of solid, say a crystalline solid, we tell what is a crystal structure. It has a lattice and it has motif. Motif is nothing but atoms. Lattice plus motif equal to. So, a solid is always associated with an underlying lattice structure, right, which is periodic in nature. right, which has translational periodicity, etc., etc. And let us assume such an lattice structure with n atoms. And we are also telling, or Einstein assumed, that each atom moves independently within the lattice in 3 dimensions. So basically, it's like a lattice gas. So you have the lattice positions occupied by atoms, and atoms themselves are moving independently. That means if I have one atom here in the lattice, say let's take a square lattice for example. Now this atom has all these 6 degrees of freedom, and it is moving independently. So this one is moving independently. It does not care about this guy's movement, this atom's movement, or these ones, right? So it does not care about whether this atom is moving this way or this way. It does not matter. It will be moving independently. That was like, and it has like, and in 3D, so it has basically, if you think of in 3D and there is this constraint, we are talking about like 3 degrees of freedom. And we are telling the next point, which is like no interactions with each other. There is no interaction between the atoms of a solid. Now that has this is a problem. This is not really a correct assumption, because then how come sound travel through solids? If sound has to travel through solids, the sound wave has to move through some medium. Now how does it move through a medium? It disturbs some atoms, that these atoms disturb the next ones, and so on and so forth, and that way the sound can travel through the solid. Now if there is no interaction between atoms in solids, then sound cannot travel. So that it's a fallacy. This assumption is not really correct. No interactions with each other is a problematic assumption. And there is also another assumption that all atoms vibrate at the same frequency. So this no interaction is one of the assumptions where we immediately can understand that that is not really true, right? Even heat transfer, the way it happens, say for example you have a hot plate made of steel is a solid, and it's like you can think of, or say some iron plate, a solid iron plate, and you are hitting say on the back side, and but you are feeling the heat also on the top, right? Otherwise cooking or many things are not possible. Now how is it possible? That means heat also has to travel through the solid, right? So if there is no interaction, how does it travel? Or sound also has to travel through the solid, how does it travel if there is no interaction between atoms? So assumption 2, as you can see, is not really correct. Sound propagation or heat propagation through solid does take place, right? Now with all these assumptions, Einstein devised a temperature called Einstein temperature. Again, he looked at a different type of statistics. I am not going to, at least in this part of the lecture, I am not going to go into the detail of these Einstein's derivations and all. But once we go into some statistical mechanical interpretation, we may again come back to it. So here, what we are telling here, that sound can propagate through solid, heat can propagate through solid. Therefore, assumption 2, which is basically atoms do not interact, is not correct, right? And now we have this thermodynamic definition, del U del V, and we define something called a theta E, which is an Einstein temperature, which is equal to h nu by kB, where nu is the frequency of oscillation of these atoms, and h is Planck's constant, and kB is Boltzmann's constant. And then we get an expression 3 NkB. So I am not going to derive the expression, but I am telling that this is some expression that Einstein got, theta I by T whole square, and theta is h nu by kB. So it's like h nu by kB T whole square, and here also there is some exponential term and stuff. What happens here is, as theta I by T, here theta I by T means h nu by kB T. When it is large, obviously you can understand that T is very small or very low, right? As you go to very low temperatures, theta I by T is very large, then you can basically approximate this exponential theta I by T by theta I by T minus 1 whole square as exponential minus theta I by T, which tends to 0, because T is very low. So this is T is very small. So this is like minus infinity e to the power minus infinity means 0. So, right, so because theta e is h nu by kb and t is very, very small, so this entire theta e by t is approaching theta e by t is approaching infinity as t tends to 0. Now, if that is so, e to the power minus infinity tends to 0, right? So, as a result, as you can see, Cv tends to 0 as T tends to 0. Now, this is Einstein temperature. As you can see, this is your Dulong-Petit law, 3 nkb, Dulong and Petit's law. And as you can see here, as T tends to 0, this is 0, approaching 0, then it increases, and then it merges with the Dulong-Petit at high temperatures. High temperatures means, here I am talking about room temperature as a high temperature. So, high temperature limit is, as you can see here, or the classical limit is theta I by t less than 1. That means t is large, right? T is large. So, if t is large, then you can approximate this as, you will see that Cv, this is something that you can prove also, because you go to this expression, t is very large, right? So, this becomes like small, so it becomes like very, very small. Here also it is small, and there is a theta e by t whole square, and there is a theta e by t. If you expand and you neglect the terms, you will basically get that theta e by t whole square and theta e by t whole square on here and here it cancels out, and you will finally get this 3 nkb. So, basically I leave the proof to you. You can try this, you can use this approximation, and you will find that Cv in such case at high temperature it becomes equal to 3R. So, you understand. So, theta e by t less than 1, that means t becomes very, very large. If t becomes very, very large, you can show that this, because if, as you know, e to the power x, you can write the series, and you can tell that, okay, if t is large, x is small, right, which is theta e by t, right. If t is large, x is very, very small. So, you do not go to x square, x cube and stuff. So, you have, for example, e to the power theta e by t, t is very, very large, so this is small. You can think of this as e to the power c, which is equal to 1. Here, you look at this can be like 1 plus theta e by t plus theta e by t whole square plus dot minus 1. So, 1 goes off, and you can tell that, okay, these terms are all neglected. So, you have in the denominator theta e by t, and here you have theta e by t whole square, and basically if you look at that, so you will see this is theta e by t, and this is over this is whole square term is there. So, you get a theta e by t whole square in the denominator, theta e by t whole square in the numerator, and as a result these things cancel out and you get 3 nkb. You can easily see that, or 3 nk where n is say Avogadro number. If I take n as Na, then Cv is nothing but 3R, which is Dulong-Petit's law. So, you recover Dulong and Petit as you go to high temperature. You recover Cv tends to 0 as T tends to 0 as you go to low temperature for solids. This is Einstein. Now, Peter Debye, he proved on Einstein model. Again, I will not go into all the detail, I will not go into the Bose-Einstein statistics and stuff, but I will tell that Peter Debye introduced something very, very important, and you must have learned it in solid state physics, and that is the concept of phonons or lattice vibrations. So, it is not like one single atom is oscillating independently of the other atom and stuff, but it is basically a collective motion of the lattice which is propagating to the material. It's like a lattice vibrations that is happening collectively. Right, so there are lots of animations of such lattice vibrations. You can see so how these lattice vibrations happen, and lattice vibrations can give different modes. But again, unlike electromagnetic waves, you cannot have like infinite number of modes and stuff. Right, so basically, you now introduce a concept called phonon, which is nothing but lattice vibration, and when there is a thermal excitation, like there is some heat input and stuff, you will start seeing that there is this excitation passes through the entire lattice as in the form of lattice vibrations. It is propagating through the material. So, if you look at that, you can define energy of one phonon as h cross omega, where omega is the angular frequency, which is like the speed of sound, effective speed of sound through the solid, and this is the magnitude of the wave vector, right? That wave that is propagated. Now, if you see that because you are having vibrations, right, oscillations, and the number of phonons is given by the statistics. I am not going to the detail of it, but one thing to note is that phonons do not have infinite modes of frequency. The modes of frequency are limited to the lattice in which we are working, right? So, it is basically related to the number of atoms that are there arranged in the lattice, right? It is basically, if you think of n primitive unit cells, then you have n modes, maximum n modes of phonon frequency. And there is a maximum allowed frequency that Debye came up with. Again, I am not going to the detailed proof of it, but later when we go to more deep into the molecular interpretation or the statistical interpretation of or the connect between statistical mechanics and thermodynamics, we may try to prove some of this. But currently, we are telling that there is definitely a molecular connect, and this molecular connect is what we are explaining. And when we are trying to explain this, remember CV, CP, all are macroscopically measurable quantities. These are like macroscopic manifestations, but all of these have an atomic or molecular origin, and that is what I am talking about. Now, if you look at Debye frequency, this is the maximum allowed for phonon frequency in a lattice, right, in a solid, and that is given by omega d, which is related to Vs, and it is also related to number density of atoms. N is the number of atoms, V is the volume, right, number density of atoms, and there is a 6 pi squared and to the power 1/3. Now, if you see that the energy is phonon energy, right, times the average, so phonon energy times the average number of phonons times the number of modes, because unlike Einstein, where he assumed like modes can be infinite, here modes are basically, if there are n lattice points or n primitive cells, then there are only n phonon modes. Now, you have h cross omega max by kb as the Debye temperature. You have a Debye frequency of omega max, which is Vs into this thing, and you have h cross omega is the energy. So, h cross omega by kb is your Debye temperature. Now, if you have that, again after some manipulation, actually Debye showed it in a very different way, but you can derive this expression in several ways by looking at, again, statistical mechanical tools, which we are not dealing with currently, but I want to tell you that the connect that you get is U is equals to this 9 kBt T by theta d whole cube and 0 to theta d by t x cube by x e to the power x minus 1 kx. At high temperature, x is small, right? At higher temperatures, as you go to higher and higher temperatures, x is basically theta d by t. So, x becomes small, right? T increases, so it becomes small. So, if x becomes small, then you basically have x cube by e to the power x minus 1. Now, if you think of this, you have x cube by x, because 1 plus x minus 1. So, x cube by x is nothing but x square, and you have t by theta d whole cube, and there is a theta b by t whole cube, and then there is a 1/3. So, it becomes, you recover again, Dulong and Petit's law, Cv equal to 3 kV of 3. And at low temperature, if you go to the low temperature, you get theta d by t tends to infinity, right? Because as you go to low temperatures, and this becomes x cube by dx by t to the power x minus 1, 0 to infinity becomes pi to the power 4 by 15, and then you have this expression of u, and del u del t is your c. So, So you basically get 12 pi power 4 by 5 n kb t by theta d whole cube. And if you plot Cv by 3 nk as a function of t by theta d, this is your Einstein curve, but this is the more correct. You can see the dotted lines is the more correct Debye curve. You please have a look at it and have a check at it, means which one is the Einstein model and which one follows the Debye curve. You can have a plot, you can plot it yourself and you can see. Remember, there is one very interesting outcome of Dulong and Petit's law. At room temperature, copper and lead both have the same heat capacity. Molar heat capacity of lead and copper are same, which is 3R. Now, if that is so, how are they different? They are different. We know that. They are different because the specific heats are different. Right? Because this is joule per mole Kelvin, which is 3R. But as you can see here, you can easily verify. If you look at the atomic mass, for example, here it is there. So, we have 3.6 for copper, lead is 207. So, as you can see here, 3R, in one case it is 3R by 207, in another case, right, is joule per mole Kelvin is this. Mole you are converting to gram. So, if you do that, so molecular weight, so or atomic weight, so 207 is for lead, right, this is joules per gram Kelvin. And for copper it is 3R by 63.6, which is for copper, is joule per gram. Immediately you can see that this is much larger than this one. So, lead has lower specific heat than copper. Lead has lower specific heat than copper. Okay, now I'll go through another very interesting observation that again can be explained from first law and from the knowledge of Cp, Cv and enthalpy, is that we will look at adiabatic flow through a valve, and this becomes very, very important for real gases, because this Joule-Thomson expansion is something that is used for refrigeration, right? It is this process, a very interesting process I will come up with, and that process is called isoenthalpic process. Isoenthalpic means we know about isovolume, we know about isobaric, we know about isothermal. Isoenthalpic means the enthalpy remains the same. Right? So, let us have a look at this adiabatic flow through a valve very quickly. So, if you look at the inlet and the outlet, and this is the system, and adiabatic means heat cannot be added to the system, cannot be removed from the system, and you have this valve here. So you press a gas here, and then you just move a piston this way, and you will see that the gas expands, and while the real gas expands, it causes cooling. This is something that we will show. So real gases, as I was telling, cool upon expansion, and this process is adiabatic. That means the enthalpy or heat content does not change, right? And then you can define a Joule-Thomson coefficient, which is eta Jt, which is del T at constant enthalpy, right? Now, again, H is a state function, so dH is an exact differential, so dH again can be written as del H by del Pt, del H by del Tp, and there are this reciprocal. So, this is something that you can have a look at. As I told you, partial differentiation, knowledge of partial differentiation is very important when you try to understand thermodynamics. And reciprocality, I think this is something that all of us know, del by del x z equal to 1 by del x del y z. And this Euler chain rule is something quite interesting. If z is a function of x and y, you can write and you can prove this del y del x z. So, del y del x at fixed z, del x del z at fixed y, del z del y at fixed x. These all, as you can see, this is a chain rule. Now, you see here del z, here there is a del z, here is a del x, del y, and this is equal to minus 1. Now, if that is so, you can use this identity or this Euler chain rule in many places. Please try to prove this. This is something that is very important and you know about this. So as you can see here, I have taken h as a function of p and t, it's like z as a function of x and y. Then I use del h del p t, del p del p h, del p del h p, and this becomes minus 1. So if you see here, you have a del p h. And what is your eta j t? It is del t del p h. So we can also use the reciprocal identity. So if I have this, so we can write del h del p t equals to minus 1 by del p del p h, del t del h p. Now this becomes minus of del t del p h, del h del p p. So dh equals to minus del t del p h, right? Del h del t p, which is Cp, and here again there is a Cp dt. So for isoenthalpic process, as you know, dh equal to 0, right? dh equal to 0, that is isoenthalpy, and you get dh equals to minus eta jt Cp dp plus Cp dt. And then because dh equal to 0, I can tell, and Cp can cancel, we get eta jt equals to del t constant, right? So you can see how we got the Joule-Thomson coefficient for isoenthalpic process, right? And as I told you that you have a gas, a real gas, this is upstream, so you move the piston this way, you compress it completely. Now downstream you are basically expanding it, right? You are just moving the piston away from, right, and the gas is allowed to expand. So PF is going in general always less than Pi, right? So PF is less than Pi, and you have isothermal compression here, and you have isothermal expansion here. And if you look at that, you have Wy, which is basically you started with a volume Vi, say for example the volume is Vi, and it goes to 0, right? We are compressing it so much that the volume goes to 0. So minus Vi to 0 PdV, which is basically going to be Pi Vi. This is work done on the system minus PdV. So and Wt is minus Pf, Vf minus 0, which is minus Pf Pf. So as you can see, the change in energy here, because it is adiabatic, is Uf, change in internal energy is Uf minus Ey, which is Pi Vi minus Pf Pf. And if you now arrange, Uf plus Pf Vf is Hf and Ui plus Pi Vi is Hi. So you can see that indeed the process is isoenthalpic. Right? So as I told, for real gases, dT, the change in temperature, is related to change in pressure. Right? So there is a Tf minus Ti, it is equal to eta Jt Pf minus Pi. Right? So, and as I told you, del T del Ph, again from our chain rule you can say that del T del Ph is nothing but minus of del H del Pt, and this is del H del Pp, and the unit obviously is Kelvin per Pascal, and all real gases have an inversion point where eta Gt changes sign. Right? So inversion temperature for oxygen, for example, is 491 degrees Celsius. So below inversion temperature, eta Jt is greater than 0. Now eta Jt is greater than 0. dP, if eta Jt has to be greater than 0, as you can see, which is del T del Ph, since dP is less than 0, right? dP is less than 0, dt has to be less than 0, and you get what is called cooling, right? If you have Joule-Thomson expansion below inversion temperature, what you get is cooling. Above inversion temperature, your eta Jt is itself negative. Now dP is less than 0, right? dP is still less, dP is always less than 0. That's what we have told, right? Pf is less than Pi, your dP is less than 0, then dt has to be now greater than 0. Now dt has to, so above inversion temperature, Joule-Thomson expansion causes warming, and below inversion temperature, where eta Jt is greater than 0, since dP is less than 0, you will always get dt to be less than 0, right? Because eta Jt, remember the eta Jt is what? It is del T del P, del T del Ph. Now if dP is negative, del T has to be negative because eta Jt has to be positive. So below inversion temperature, you will always see Joule-Thomson expansion causes cooling. Above inversion temperature, it becomes the opposite. It causes burning. So for ideal gases, if you see, as we have already mentioned very quickly, pi T equals to del U del V T. And if you see this del H del P T, if you look at the proof here quickly, del H del P T is del U del P T plus P del V del P T plus V. Now you have del U del V del P, this is from chain rule. So this you are writing as this minus P nRT by P square plus V. Now nRT by P square is nothing but nRT by P is nothing but V. So minus V plus V becomes 0, and this guy del U del V itself is 0. So as a result, eta Jt for ideal gases is equal to 0. Right? So from next class onwards, I will start with the reversible. I will just tell one or two more important points of reversible adiabatic expansion. Then I will start with the second law. Right, so we will start with the second law. So we look at the reversible adiabatic expansion because we just want to know what is we know the Cp minus Cv, but what about Cp by Cv, and this is why does it become useful. So we will look at reversible adiabatic expansion in the next class. But remember, this Joule-Thomson expansion coefficient eta Jt for ideal gases is 0. Okay, so if you have any questions, please post those questions to us. And we will have a look at. If you have any doubt, we will try to get back to these emails, and we will try to